Hello, and welcome to Module 4, Lesson 22 for 8th grade. Today we are going to talk about constant rates again. I know this was a topic that we visited in the beginning of the unit, and we are going to revisit it now that we have a better understanding of slope and y-intercept and graphing all of those things. So the first thing I'd like to write down in our notes here as clarification is that the word constant rate is used a lot here, and that is the same actually as slope and also as rate of change. It's just like the words great, awesome, super. They all mean the same thing. Same thing here in math. Constant rate and slope and rate of change all mean the same thing, and they interchange them quite a bit as you go through your mathematical career, and even just in this text. So that's something that we need to just kind of work on, using all of those vocabulary terms. Okay, so I want to start on page 131, and I just want to walk through a few examples. What we're going to end up doing here is write some equations and then learn how to use the graph and use our equations to help us, and also to compare the different rates here. So let's start with exercise 1. It says Peter paints a wall at a constant rate of 2 square feet per minute. Assume he paints an area y in square feet after x minutes. Express this situation as a linear equation in two variables. Anytime we see this word linear equation, we are looking to get y equals mx plus b, meaning we want this format where m is our slope or our rate of change or our constant rate, and b is our y-intercept or our starting amount. So in this situation, we have y equals our m, our constant rate, is 2 square feet per 1 minute. So we're going to use 2 over 1 for our slope, our rate of change, and then we'll put that times x, plus now our b, our y-intercept, or our starting amount. You have to kind of think of this in terms of the situation. If he paints for 0 minutes, then he's not going to paint any square feet, so our y-intercept is 0. So here's our linear equation. Y equals 2 over 1x plus 0, or if you could simplify that, y equals 2x. Okay, now we want to sketch a graph of the linear equation. And again, this is a review. So now that we know this, we can start with our y-intercept, or our starting amount, which we've decided was 0. Okay, so 0, 0. And then we're going to use our constant rate, or our slope, to get the next point. So our slope was 2 over 1. So we're going to start at 0, 0, and we're going to make a dot there. And then our slope says positive 2, so up 2, and positive 1, so right 1. Notice that the scale is going by 2's here, which is why I actually only went up 1 square, but that counts as 2. And then we are going to draw a line as carefully as we can. We should use a ruler, although I'm not, because I don't have one available right at the moment, all the way through the graph. And you want to make it all the way through because the following questions usually have to do with using that graph then on numbers that are not these first two. So as I just said, the next question says, using the graph or the equation, determine the total area he paints after 8 minutes, 1.5 hours, and 2 hours. Okay, so let's start with 8 minutes. If we look at our graph, 8 minutes is right here on our graph. So we can use just our graph, follow it up to our line here, and this is where it hits, and follow it over, and it tells us that for 8 minutes, he paints 16 square feet. And that was using our graph. Now, 1.5 hours is actually 90 minutes. And obviously our graph only goes to 8 minutes. So we can't use the graph unless we want to extend it out 82 squares, which I really don't want to do that. So if that's the case, that's when we use our equation. So our equation was y equals, and I'm going to use the shortened version, y equals 2x. And what I'll do with this 90 minutes is I'm going to insert 90 into the x part. So really, to get my answer here, I'm going to say y equals 2 times 90, which means that our y equals 180 square feet. So in an hour and a half, 1.5 hours, he can paint 180 square feet. Okay? And you would do something similar for 2 hours, which I'll let you do. Let me remind you, though, that 2 hours, we're not working in hours, we're working in minutes. You would have to convert that to minutes first and then put it in your equation. Okay, so that's example 1. I want to go over one more example, possibly 2. We'll see how long this video gets, to show more of how we're going to use these constant rates. So if you turn the page, you have number 2. So now I'm actually on page 132, and it says on here, it starts with a graph this time. It says the figure below represents Nathan's constant rate of walking. Part A says now, Nicole finished a 5-mile walkathon. It took her 1.4 hours. Okay, I first want to point out that this is Nathan's graph, but now we are switching to talking about Nicole, a totally different person. So she walks a 5-mile walkathon in 1.4 hours. Assume she walks at a constant rate again, so we're going to get a slope here. That's what that means. Let y represent the distance Nicole walks in x hours. Describe Nicole's walking at a constant rate as a linear equation. Again with linear equation, meaning we're going to use y equals mx plus b into variables. So now what we want to replace m with is the slope for Nicole, the rate of change, the constant rate. So she walks, I'm going to start my y equals, she walks 5 miles in 1.4 hours. So here's my rate of change, or my slope, times x, I'm going to put the time sign in this one, plus b, meaning plus where she started at. So let's think about this again. In 0 minutes, she walks, or 0 hours, excuse me, she would have to walk 0 miles. So again, we're starting at 0. So here's our linear equation. This is the answer to A. Now the second one, we're like, what's going on with Nathan up here? Well, that's where we're going to be. It says now who walks at the greater speed? Is it going to be Nathan with this graph or Nicole with our equation? And here's what we're talking about. Speed of something is always referring to our slope or our rate of change. So Nicole, we're going to use, we know she walks 5 miles in 1.4 hours. This is Nicole. Well, how fast does Nathan walk? What's his rate? Remember, slope is rise over run. So we're going to start by making 2 points. I'm going to make one at 0, 0 and one at 1, 4. And my rise then, so my slope or my rate of change here for Nathan, my rise is 2, 4, so up 4. And my run is 1. So he walks 4 miles in 1 hour. It's still not obvious though, and this, I'm going to label this, this is Nathan. It's still not obvious who's faster. And if that's the case, what you're going to have to do is use your calculator and divide. Well, the first one's pretty easy. 4 divided by 1 is 4 miles per hour. Okay, so Nathan's at 4 miles per hour. Nicole's not as obvious though, so if you get your calculator out and you divide 5 by 1.4, it tells us that Nicole walks at about 3.57 miles per hour. Now we can make that decision. Who walks faster? Is it Nathan at 4 miles per hour or Nicole at 3.57? And that would be Nathan. Nathan walks at a greater speed because his slope or rate of change or constant rate is greater. Okay, and the following lesson is, oops, sorry, you can't see that, is going to be all based on this. It's all based on finding the slope or rate of change of two separate things and then comparing them to see which one is larger or which one is faster. And it helps you to be able to divide the slope out if you have a rise over a run. And then sometimes it's a little more obvious when you divide it out and you can see, okay, well, this one's bigger than the other one. For the sake of the video, this is where I'm going to stop. There are two more examples, which I will gladly go over with you if you want to come in at a later time or in the morning or at lunch. And the assignment today then is going to be page 135, numbers 1 through 5. Okay, have a great day, and hopefully that explains it.